We are going to begin today with one last reduction reaction. So this is one I realized that we didn't quite do last time. You've learned that reduction in organic chemistry can often involve either a decrease in the number of carbon heteroatom bonds or an increase in the number of carbon hydrogen bonds. And so you might have been thinking, what about using H- as a nucleophile? I'm going to put this in quotation marks, but somehow adding H- to an electrophile might be a way to do a reduction. Now, you've encountered a reagent before where H- was involved, and this was sodium hydride. But you can't use sodium hydride for reductions. Let me tell you why not. Sodium hydride, as you know, is just sodium plus as a counter ion and H- as the base. Sodium hydride is a good base. It's the conjugate acid of hydrogen gas, which has a pKa of 35. So it's a very strong base. However, it is not a good nucleophile. That's weird, but you'll find that your text never really uses it as a nucleophile when you want to add H- to something. A quick sort of back of the envelope explanation is the poor solubility of NaH in organic solvent. Meaning when you put NaH in organic solvent, it mostly sits down at the bottom of the flask as a powder, and H- never really dissolves or floats around in solution. So if a molecule wants to react with H-, it's got to get up really close to the solid. The solid can approach protons okay, but really can't attack carbons. So even though H- is really small, NaH is like a huge sterically hindered base. So we're never going to use it as a nucleophile. So what about a nucleophilic version? What about a nucleophilic source of H-? And the new reagent is something that we'll only touch on briefly in 351, but which will come up a ton in 352. And this is a reagent called lithium aluminum hydride. So lithium is the spectator counterion, and aluminum hydride is aluminum forming 4 bonds with hydrogen with a negative formal charge on aluminum. You'll notice that aluminum is from the same column of the periodic table as boron, meaning that when aluminum's bonded to only 3 things, it should be neutral, but when it's bonded to 4 things, it should have a negative charge. And now you may be beginning to see how this is a hydride carrier or hydride delivery reagent, because if aluminum hydride could hand off an H-, it could suddenly be neutral instead of negatively charged. Another thing that tells you why aluminum hydride is a hydride delivery reagent is that aluminum is, like boron, less electronegative than hydrogen. So actually, the negative formal charge on aluminum is felt more on these adjacent hydrogens. Okay? So lithium aluminum hydride, I think of it as a hydride delivery reagent. It is soluble in organic solvent so that it can approach electrophiles and deliver H- to an electrophilic carbon. Another thing you need to know about lithium aluminum hydride, this isn't really a detail to memorize, but being aware of it can be useful in 352. Lithium aluminum hydride though it's a hydride delivery reagent, is also relatively basic. So you can't use protic solvents. If you use protic solvents like water or alcohols, lithium aluminum hydride will deliver a hydride to remove a proton from the alcohol. You'll generate hydrogen gas. If you're not careful, you'll start a fire because the reaction's pretty exothermic. So in practice, if you go in the lab, if you're like, hey, Professor Castle, I was hoping to do a lithium aluminum hydride reaction, they're going to say, whoa there, buddy, slow down and let's teach you how to do it because it can be dangerous to do. In any case, we're not going to be doing actual reactions with lithium aluminum hydride in this class, just on paper, so knock yourself out. Use it as much as you want. So we're going to use lithium aluminum hydride as a reagent in an epoxide reduction reaction. I don't know that you need to memorize the name of this reaction, epoxide reduction reaction, because I think you can basically figure it out. It's going to be opening of an epoxide with a strong nucleophile. You learned how to do that in chapter 9, only this time the nucleophile is going to be lithium aluminum hydride. So let's give you a brief example of this. Here's an epoxide with carbons A and B. Because our nucleophile is a strong nucleophile and because we are not protonating the epoxide first, we're going to open the epoxide at the less substituted carbon. The mechanism is going to be SN2 and sterics are going to dominate. Remember that if you were to protonate the epoxide first, you get the opposite result. But guess what, folks? Because putting lithium aluminum hydride in acid starts a fire, we're never going to protonate the epoxide first and then use lithium aluminum hydride. We're always going to react lithium aluminum hydride with the neutral epoxide. So the way you push arrows for this reaction is literally hydride leaves from aluminum and gets handed off directly to less substituted carbon A, and then we break the bond between carbon and oxygen. Recall that in an epoxide, OR minus can leave because you're relieving ring strain. The carbon A now has 3 hydrogens attached to it. Carbon B is now negatively charged. So that's the first step. And then usually in the second step, when people are using lithium aluminum hydride as a reagent, usually they will specify a second step where they use water. This is basically just aqueous workup. So when you see water as item 2 on a list that begins with lithium aluminum hydride, it's not mysterious what the water is doing. The water is protonating the negatively charged oxygen using water. So you can reduce the epoxide. How can you tell that it's reduced? Because there's one more CH bond in the product than there was in the starting material. Okay, questions? Yeah?
So if we can't have it in a protic solvent, how do we have it? Do we just put it in water after that first?
Yeah, so what you do is you add enough lithium aluminum hydride, only enough to do the reaction. You consume it all, and then you add water, and then you're okay. Or if there's leftover lithium aluminum hydride, you add water slowly and you keep it cool. Yep. Now, just as a preview, not as something you're going to be responsible for yet, but just as a preview, you can use lithium aluminum hydride to reduce aldehydes, ketones, esters, etc. I'm just going to show you one of these. You're not responsible for it because it's 352, but you will see in 352 that lithium aluminum hydride can deliver a hydride to the pi star of a ketone to reduce the ketone to an alcohol, and then if you add water to the alkoxide, and then if you add water, you can protonate the alcohol, and you can reduce the ketone overall to a secondary alcohol. So that's 352. We'll talk about it then, but you've been introduced to the reagent here. Anything more we need to say about that? All right, so let's talk about how to form epoxides in the first place. You've already got one method to do this. You learned it, I think, on problem set 9. The idea here is that you take an alkene, say this cis-alkene, you do halohydrin formation, that's a chapter 10 reaction. That delivers Br to one side of the original pi bond and OH to the other side of the original pi bond. We would get the enantiomer as well. And then you learned an interesting reaction where if you take a strong base that's not a good nucleophile, like sodium hydride, you can remove the proton from the alcohol, and then what you have here is a nucleophile, negatively charged oxygen, and a leaving group on the same carbon, or sorry, in the same molecule on adjacent carbons. And you can see that they're on opposite sides of this molecule, such that the oxygen can do backside attack in an SN2 fashion to give you this epoxide, which I could draw like this, or could just as similarly draw like this with the two methyl groups cis to each other. Okay? You've learned that. Go ahead.
So we're not, since you said we don't use NaH for reduction, this isn't a reduction, right? This is just like what we...
This is just deprotonation.
Okay, got it.
Yep, you can totally use NaH for deprotonation, but not for reduction. Yep. Okay, so that's a two-step method for making an epoxide, and it works, and you've practiced that before on the problem set. If you didn't or didn't understand it, you should go back and look at that. But now we have a direct method, one step. And as I told you, why are we bothering if we already have a method? Because organic chemists race to have the most efficient synthesis to get a molecule. And actually, this is a problem that has real dollar implications. When you go to synthesize a drug and you need to make metric tons of it, efficiency is really important. And if you save money in the synthesis and make it more economical, then the company's more profitable. So a one-step method is better than a two-step method, or can be if the reagents are cheaper and easier to deal with. So the reagent that we need to introduce is called metachloroperoxy benzoic acid. This is going to involve a functional group that you've never seen before. So that's kind of cool. Here is the chloro, and then here is a carbonyl group with an oxygen. If this were a carboxylic acid, we would put a proton there, but it's not a carboxylic acid, it's a peroxy acid. So peroxy refers to an oxygen-oxygen sigma bond. So this is a peroxy acid. It's like a carboxylic acid, only you've inserted another oxygen between the carbonyl and the OH group. Oxygen-oxygen sigma bonds in peroxide or peroxy groups are relatively weak. They're subject to nucleophilic attack, and they're really good for oxidation chemistry. You may have encountered peroxide type bonds before if somebody's ever taken a bottle of hydrogen peroxide and rubbed it on a wound of yours to clean the wound. The peroxide oxidizes bacteria too, and then they die. The stuff that they were putting, that you can buy at like a pharmacy is like 3% hydrogen peroxide in aqueous solution. That's not enough to burn your skin. 30% hydrogen peroxide is enough to totally burn your skin and bleach your clothes, and you don't want to do that. So anyway, we don't like writing out long words in organic chemistry, so we often come up with acronyms. mCPBA. So, and if you want to just know mCPBA or memorize that acronym, you're good. Popular question at this stage of the course: do you want us to memorize the structure of mCPBA? You need to know enough of it that you can draw a reasonable mechanism. This is the business end of the molecule. This over here you can think of as an R group and just sort of ignore. All right? So let's show you how this reaction works. I'll just give you the same cis alkene. And we'll use mCPBA. mCPBA generates the same epoxide that we saw above, but in a single step. And the oxygen that gets delivered to the epoxide is this one that I just colored in orange. So it's that oxygen, the one that's on the end, the one that's bonded to the other oxygen, that gets transferred. This reaction is concerted, and it's stereospecific in the sense that the stereochemistry of the starting alkene determines the stereochemistry of the resulting epoxide. That is, if I start out with two groups that are cis to each other in the alkene, those two groups must be cis to each other in the epoxide, and two groups that are trans to each other in the original alkene must be trans to each other in the epoxide. Okay? Got that stereochemical issue down? So let's deal with mechanism. I want you to think about this mechanism by analogy to another three-membered ring-forming reaction that you've done before. If you remember the bromination reaction mechanism, where we had an alkene like this, pi electrons attacked a weak heteroatom sigma bond, leaving group left, and then lone pairs on the first bromine attack the other carbon to give us a three-membered ring intermediate. We're going to do something very similar with mCPBA, only the thing that leaves is going to be just a little bit more complicated. You're going to sort of hate this, but on the other hand, it's all in one step. There's a lot of arrows, but at least it's all in one step, and you don't have to draw out intermediates. So what I'm going to draw now, look for analogies to what we drew previously for the bromination reaction. All right, so here's the alkene, same starting material. You're going to draw the orange oxygen, the one that gets attacked here. Put the hydrogen here, the other oxygen there. Then this is going to be the carbonyl group, and then this is the R group, the rest of that molecule. And you're going to need a lone pair on that carbonyl oxygen and a lone pair on the terminal oxygen. This is going to be, just as over here, the orange bromo was the one that was attacked. That oxygen is going to be the thing that gets attacked. And then this is the weird part. All of this is the leaving group. Now you're like, okay, chuckles. The hydrogen is not even attached to the leaving group, so how are you going to do that? And stay tuned. That's the arrows that we're going to push, okay? So the first few arrows should look familiar. Pi electrons attack the weak, attack the low energy oxygen sigma star, because heteroatom bonds are weak. That's exactly analogous to this arrow in bromination. At the same time, lone pairs on that orange oxygen are going to attack the other carbon. Those are the arrows that make the new epoxide bonds. Everything else is going to be leaving group leaves, okay? So what we do now, we're going to talk about conceptually first before I draw any arrows, and then I'll draw the arrows. If you attack a sigma star, the sigma bond's got to break. So that would mean these electrons go on this oxygen, right? If we did that, conceptually that would give us a protonated epoxide and then would give us a negatively charged carboxylate, which could then deprotonate the epoxide and like this and give us the product, right? The thing is, we don't have to do it stepwise like that, in part because this atom, the carbonyl oxygen, is very close in space to this hydrogen. So I want you to imagine once this bond breaks and goes onto this oxygen, and that oxygen's negatively charged, can you see that that leaving group would be a carboxylate? And can you see that the other oxygen would share that negative charge by resonance? So it would be not such a stretch for that negatively charged oxygen to be the one that does the deprotonation, right? So we're going to show that all in one step. These electrons kick down and form a pi bond, and then these electrons kick over and remove the proton. You can either show it like that, or if you want more arrows, you can show it like this. Either way, you got the same thing. And then the bond between the hydrogen and the oxygen breaks. So, oops, didn't want the undo arrow. Electrons from the sigma bond form a pi bond here. Carbon-oxygen pi bond breaks. Lone pairs on the oxygen. Or, again, if you wanted to do if you wanted to show the pi bond directly coming and attacking this proton, that's fine too. Then the hydrogen-oxygen bond breaks. Okay, so that's the one-step mechanism. Some people have called this a butterfly mechanism because if you turn it to the side, so looks like something, but I don't know. Anyway, one step mCPBA, okay? So that's a useful reagent. You should remember it. Now, epoxidation can be part of a useful two-reaction sequence. It's not really anything new, and you should totally be able to do it based on what you learned in chapter 9. But here it's grouped together in your text in part to serve as a contrast for what's coming next. The two reaction step series is called I needed a di before hydroxylation. Anti-dihydroxylation. As you can see, organic chemists are fond of words that end in ation. In part because they describe what the reaction's going to do. And if you remember those words, they can help you with synthesis. Here, the effect of the reaction will be to add two OH groups in place of a carbon-carbon pi bond, and they will be anti to each other relative to the original alkene structure. So, to demonstrate this, let's start with a cis-alkene. The first step is mCPBA, which, as you know, gives you the cis epoxide, and then you can open up the epoxide actually under acidic or basic aqueous conditions. Either will work. For dihydroxylation, it doesn't matter. And the product will look like this. If you draw, and of course we will get its enantiomer. if you draw the carbons that were in the original alkene in the same general orientation as they were in the original alkene, then you will see that the oxygen from mCPBA and the oxygen from hydroxide end up on opposite sides. They are anti to each other. And that term anti refers to the original structure of the alkene. Notice, and this is a trick, the dastardly trick I showed you last time, by rotation around carbon-carbon bonds, I can redraw this same structure like this. And that, if you're moving too quickly and don't understand that it's an anti-dihydroxylation, you might be deceived into concluding that the starting material was the trans alkene, which it isn't, right? Yes? No? Yes? Go ahead.
So if they are both wedges, we should assume that it's been rotated in some way?
If you're thinking about using anti-dihydroxylation, that is this two-step reaction sequence, and the oxygens are both wedges, then yeah, you need to rotate it so that one's a dash and one's a wedge. Okay. Similarly, let's start with the trans alkene. We'll use mCPBA to make the epoxide. This epoxide is chiral, so we have to also have made its enantiomer. But you'll see then that if we open it up in the second step with hydroxide and water, we will get an anti-dihydroxylation product that will look like this. I'm going to draw the carbons in the same orientation that they were in the original alkene. And then I'm going to show the anti-dihydroxylation product by having the OH groups be pointing to opposite sides. Now, let's just clarify here. Remember, it's relative to the original alkene, which is flat, right? Planar in the plane of the page. So one oxygen gets added from above, the other gets added from below. This one is a wedge, this one is a dash. It doesn't matter that this one's pointing to the top of the page and this one's pointing to the bottom of the page. It's anti-dihydroxylation because one is a wedge and the other's a dash. And notice that I can again try to deceive you by drawing the molecule like this, where the OHs look like they're on the same side, but I haven't drawn the carbon chain in the orientation that it was in the original alkene. Yeah?
So it doesn't matter if you drew like the enantiomer, it's just a meso compound.
If it's a meso compound like this is, there's no enantiomer to draw. Yep. Or if you attempted to, it would just be the same thing. Yeah?
Is it possible to make an epoxide to where both of the bonds from the oxygen one is attached to the wedge?
Is it possible to make an epoxide, draw an epoxide such that one bond to oxygen is a dash and the other is a wedge? I think you could do it, but and it would probably communicate, you could probably communicate correct stereochemistry, but it's kind of weird. A three-membered ring has to be a plane. It's got three atoms in it. That defines a flat space. So it would be kind of weird to do that. Yeah.
Will things still be like attacking it the more substituted
Yeah.
in like when it's asymmetrical?
If it were asymmetric, would the negatively charged oxygen still be attacking at the more substituted carbon? Yes. If you were using acidic conditions, it would be. Let's back up. Would this strong nucleophile be attacking at the less substituted carbon because it's a strong nucleophile and we're not protonating the epoxide first? If there were a difference in substitution, yes. However, you can't tell because both of the things that end up on it are oxygen. So you can't tell after the fact which one was the epoxide oxygen and which one was the hydroxide oxygen. Similarly, if you used acid and water to open up the epoxide, you would expect that you'd protonate it first and then water would attack the more substituted side. But again, you could not tell from the product because both things that end up on the atoms are oxygens.
Okay.
Yep, go ahead.
This is probably something you answered earlier, but I just wanted to get a question for my notes. On how we got the stereochemistry of the products based off of the alkene being cis or trans. So like on the cis alkene, we had a dash and a wedge OH as opposed to on the trans alkene.
Yep, that happens because, and maybe it would have been better for me to draw this epoxide in a slightly different way. I could have drawn this epoxide with the groups here, both wedges. The reason that the OH that comes in and attacks gives you a dash instead of a wedge is because this is opening up of an epoxide is SN2 with backside attack and inversion of configuration. Okay, yes?
I'm having trouble seeing, I've seen in a few things that they just change, whether the wedge or the dash is on, like on the O or on the bottom. How are you switching between them? And when is it like advantageous?
So, these two drawings of the epoxide, I think are what you're referring to. They are the same thing. It's just a matter of perspective. If you take the molecule on top and you tip the orange oxygen back into the plane of the page, that's going to pop those methyl groups out towards you. Yep. So there are two drawings of the same thing, and yeah, both of them are fine. All right, so you need to be able to follow that through. If I show you a product like this, and I say, what was the starting material if the reagents were mCPBA and NaOH afterwards? You need to be able to think backwards to the correct alkene structure. All right? Now, shall we make it worse? No, that's the answer in this class is always. There's always more, all right? So now we're going to learn a method for syn dihydroxylation. Right? This is going to be a method that gives us, we're going to add two OH groups in place of a carbon-carbon pi bond, but they are going to be syn or cis to each other relative to the original alkene. Now this is a reaction whose mechanism we're not going to learn in detail. We could talk about it, and maybe I'll show a little bit of it for you if it might help you to remember what's going on. If you want to just memorize it, that's okay. This will also function with alkenes. It's also a two-reaction series. The first reagent is osmium tetroxide. OS, osmium, is a transition metal. And then the second step involves an unusual sulfur-containing salt called sodium sulfite and water. And it's not clear, nor is it really shown in your text, what the sodium sulfite does. I will try to illustrate it briefly, but you can just memorize that this gives you syn addition of two OH groups onto the same side of the original double bond. That is, if the original double bond was cis and you draw the carbon chain in the same orientation in the product, the two OH groups have to be both on the same side. Yeah?
Does this only work for cis alkenes?
Nope, it works for trans as well. Yeah. It works for trans as well, and I'll show you that in just a little bit. Osmium tetroxide, I don't care that you know the structure of that reagent, but I will show it to you here. It's a pretty electrophilic reagent if you calculate, and I haven't shown you how to do this, nor will I, but at least not until 352. This is osmium in the +8 electron state. So it's +8 oxidation state. So it is highly electron poor. It is a very strong electrophile. And I will just show you briefly, without a lot of explanation, how the first step of the reaction goes. It's a single concerted step. The pi bond attacks the oxygen, electrons go onto the osmium, and then another oxygen attacks the other carbon. You end up with an intermediate that looks like this, where the two oxygens have been added to the same side of the original alkene. These are the two oxygens that are going to stay in your product. You don't need to know this, but this intermediate is called an osmolate ester. And the second step is about hydrolyzing that ester to release the diol. Okay? So, as I said, you don't need to know this mechanism. There are alternative conditions for syn dihydroxylation in your text. There's another reagent called KMNO4. You don't need to know that. I won't hold you responsible for that. It does essentially the same thing. I don't need you to know how to make the osmolate ester. I don't need you to know the mechanism for hydrolyzing the ester. I do need you to know how to predict the products, how to get the stereochemistry right, how to know, I do need you to know what the right reagent is. Yes?
If you just show us the product, how do we know whether it's the result of syn dihydroxylation or anti-dihydroxylation?
Right, so I think you're pointing out that if we were wanting to get the meso 1,2 diol, there are two methods for it, right? I could have either started with the trans alkene and done anti-dihydroxylation, or I could have started with the cis alkene and done syn dihydroxylation. And that's absolutely true. And in fact, on alternative problem set 10, I think I have a problem I put on there where I say, hey, you can do this via two methods. Can you find both of them? One of them is okay, but if you can find both of them, and it involves this kind of thing, that you can get the same meso 1,2 diol using either syn or anti-dihydroxylation as long as you get the starting alkene stereochemistry right. Just to complete the thought, let's show you the product of syn dihydroxylation on a trans alkene. The way you're going to show this is, again, to draw the alkene, draw the carbons in the product in the same orientation as they are in the alkene starting material, and then put the two OHs on the same face of that original alkene, in this case both wedges. This ends up being chiral, so you need to have also made its enantiomer. And then be advised that you could totally redraw the molecule and make it look like this, and that might conceal the fact that if you use osmium here, your starting material must be the alkene. So be prepared for a question where I show you a product that looks like this, and the reagent is osmium, and then I ask you to figure out what the original alkene was. Okay? All right. So now we need to finish our chapter 11, and probably we won't get to all of it. We'll need to spend a little bit of time next time, but we're going to finish up by talking about oxidation of alcohols. And this is really important because these reactions are very useful in synthesis, and also biology does these reactions, not with the reagents we'll use, and you won't learn till 352 how biology does some of these oxidation reactions, but you need to get used to the idea that you can oxidize alcohols to other things. So, as I mentioned at the beginning of this chapter, you can oxidize a primary alcohol to an aldehyde And you can tell that it's oxidized because we've decreased the number of carbon hydrogen bonds and increased the number of carbon heteroatom bonds. You can also oxidize the aldehyde further to the carboxylic acid. One requirement for oxidation, though, is that the carbon that has the oxygen on it must also have CH bonds. As long as there is a CH bond, there is still a chance for oxidation. So, if we start with a secondary alcohol where there is only one CH bond, we can oxidize a secondary alcohol to a ketone, but there we are stuck. There's no additional oxidation using the reagents that we'll talk about today, because there's no additional CH bonds. Similarly, you would expect that if you had a tertiary alcohol, you can't oxidize because there are no CH bonds on the tertiary carbon. All right? So we'll be learning today about oxidation of primary and secondary alcohols. We will learn one reagent that can take the primary alcohol. Excuse me. Gonna sneeze. All right, we will learn one reagent that can take the primary alcohol and oxidize to an aldehyde and stop there. That same reagent will also oxidize a secondary alcohol to a ketone. And then we'll learn another reagent that will take the primary alcohol, go to the aldehyde, but not stop there and go all the way to the carboxylic acid. And this is summarized in detail in your study guide, but we'll talk through it here. Let's start with the reagent that can stop at the aldehyde. So this reagent is called pyridinium chlorochromate. And because we get tired of writing out long words, this is called PCC. The pyridinium portion is a 6-membered ring containing a nitrogen with double bonds like that. The nitrogen's protonated. This is a spectator counterion. It helps things be soluble, but it isn't going to be involved in the mechanism. The real thing that does the oxidation is the negatively charged portion, and this is the chlorochromate ion, and it has chromium in the middle. Chromium is a transition metal, and chromium is in the +6 oxidation state. So again, chromium is very electron poor, and it is the electrophile. And importantly, you can see that chromium has a good leaving group on it, and that's going to be important to what we're going to do. So let's start with the mechanism of oxidation of a primary alcohol to an aldehyde using PCC. Lone pairs on the oxygen act as a nucleophile to attack this highly electrophilic chromium reagent, and chloride leaves. That gives you an intermediate that looks like this. Oops, I think I wanted to do it differently. With a negative formal charge on the oxygen on chromium and a positive formal charge on the protonated oxygen. Now, your text at this stage will do something that I find kind of lazy. I'm kind of inspired by it, but also irritated and also sort of jealous. Your text will just do this: proton transfer. Thanks for that. and we'll just draw this as the product, and they will call this a chromate ester. Now, the reason that they're doing this is it makes sense that if this oxygen's negatively charged and this one's positively charged, that we could save ourselves some time by just moving this proton over onto that oxygen. And if you want to see how you would do that with arrows, lone pairs on this oxygen attack this hydrogen, and then the electrons go onto that oxygen. I don't like that because I know some things about organic chemistry, and that it's hard for an atom that's only 4 bonds or 3 bonds away from another atom. It's kind of hard for this to actually reach over and get to the antibonding orbital that it would need to access. So this looks reasonable, and it's short, so we're going to keep it. But my preferred thing, and what I've actually done on the key to problem set 10, is I will have a base remove this proton first. I'll draw an intermediate, and then I'll have this oxygen pick up a proton from an acid. Yes?
Do we need to know this mechanism? Because I know you showed us the same dihydroxylation. Like, do we need to know this?
Yes, this one we're spending time on. Yes, you do need to know this mechanism. Okay, so at this state, once you get to the chromate ester, I'm going to tell you that this group with the electrons in that oxygen chromium bond is a good leaving group. Now you're going to say, how would I have known that? And the answer is you wouldn't, and that's why I'm the professor and you're the students. So I'm telling you now. I actually wouldn't have recognized that as a good leaving group either, other than that it happens and it leaves. So sorry for that. That's sort of the best we can do here. So what happens is if you've got a good leaving group on the oxygen, which we're going to call alpha because it has the good leaving group, on the adjacent atom you have a proton. And so we can proceed to do an E2 style elimination reaction. And it doesn't take a very strong base at all. If you're paying attention to what negatively charged things we have in solution, it could be Cl minus. I don't like that because Cl minus is not a great base. Maybe it's the negatively charged oxygen from one of these other intermediates. If you'll allow me, we don't have to add an extra base. It's just some molecule in the reaction that's going to act as a base, removes this beta proton, electrons kick down, and leaving group leaves. And if you follow, we've lost a hydrogen, we've gained a CO pi bond, and then the leaving group is this, and this is going to be a byproduct that we're going to just forget about it. But this is the reduced form of the chlorochromate starting material. And if you counted electrons, you would see that in effect, these 2 electrons that used to be on the oxygen and then were in the oxygen chromium bond, they leave with the chromium. So that's where the electrons went. That's the loss of electrons that we've talked about before with oxidation. Okay, that's enough for today. We'll finish chapter 11 up on Friday and move on to chapter 12.